Dear children, in the last class we have studied about structure of atom. In that class we studied J.J. Thomson atomic model, Rutherford atomic model, Bohr's atomic model, and also studied about Sommerfeld's model of atom. To know the properties of electron in an atom, a quantum mechanical model of atom was developed by Erwin Schrödinger. What he said? According to Schrödinger's quantum mechanical atomic model, the electrons exist in a particular region of space around the nucleus at a given instant of time is called orbital. Children, you can find here the definition of orbital: the region of space around the nucleus where the probability of finding the electron is maximum is called orbital. In some places we cannot find a electron. The region of space around the nucleus where the probability of electron is 0 is called as a node. In a given space around the nucleus, only certain orbitals can exist. Each orbital of a stable energy state for the electron is described by a particular set of quantum numbers. Children, what are quantum numbers? Before going to the quantum number, here you need to understand one point, that is, according to Bohr, electrons are revolving around the nucleus in orbits, but Schrödinger said that there is no boundary, there is no particular path to revolve around the nucleus for the electron, but electrons can be identified in a certain area or space. That space is called orbital. It means Schrödinger has introduced the concept of orbital. To know about the orbitals, we required the quantum numbers. To know the position of electron in an atom, we required these quantum numbers. Now let us learn what are the quantum numbers. Quantum numbers indicate the probability of finding the electron in the space around the nucleus. Each electron in an atom is described by a set of 4 quantum numbers. We can get complete information about all electrons in an atom, that is location, energy, type of orbital occupied, shape and orientation of the orbital, etc. Children, there are 4 quantum numbers which help us to find the position of electron. Children, one point you remember here, quantum numbers are just like postal address of electron. To find a person, how we required a postal address, in the same way quantum numbers are postal address for the electron, and there are 4 quantum numbers. That quantum numbers are principal quantum number, angular momentum quantum number, which is also called as the azimuthal quantum number, magnetic quantum number, spin quantum number. Children, principal quantum number was introduced by Niels Bohr, azimuthal quantum number was introduced by Sommerfeld, magnetic quantum number was introduced by Landé, and spin quantum number was introduced by Uhlenbeck and Goudsmit. Now let us learn about principal quantum number. The principal quantum number is related to the size and energy of the main shell or orbit. The values of n are 1, 2, 3 and so on. As n increases, means principal quantum number increases, the shells become larger and the electrons in those shells are farther from the nucleus. An increase in n also means higher energy. It means n value increasing means energy of the orbit also increases. N is equal to 1, 2, 3 so on are often represented by the letters like K, L, M, N and so on. For each n value there is one main shell or main orbit, and the second one is angular quantum number. It was introduced by the Sommerfeld. It is also called as azimuthal quantum number. and which is represented with L. Angular momentum quantum number is related to the shape of particular subshell in the space around the nucleus. Angular momentum quantum number has integer values from 0 to n minus 1 for each value of n. Each L value represents one subshell. The value of L for the particular subshell is generally designated by the letters S, P, D, F and so on as follows. See here in the table it was given, if L is equal to 0 then it is S subshell, if L is equal to 1 then it is P subshell, if L is equal to 2 then it is D subshell, if L is equal to 3 then it is F subshell. If L is equal to 0 then the name of the subshell is S, if L is equal to 1 then the name of the subshell is P, if L is equal to 2 then the name of the subshell is D, if L is equal to 3 then the name of the subshell is F. L is equal to 0 then it indicates S orbital, if L is equal to 1 then it indicates P orbital, if L is equal to 2 then it indicates D orbital, if L is equal to 3 then it indicates F orbital. When n is equal to 1 there is only one subshell, that is 1s orbital, and that value indicated as 0, L is equal to 0. This is designated as 1s orbital. When n is equal to 2 there are two subshells, in that with L is equal to 0 2s subshell, with L is equal to 1 2p subshell. Similarly, when n is equal to 3 there are three subshells, like L is equal to 0 then it is 3s subshell, with L is equal to 2 then it is 3p subshell, with L is equal to 3 then it is 3d subshell. Similarly, when n is equal to 4 there are four subshells, with L is equal to 0 4s subshell, with L is equal to 2 4p subshell, with L is equal to 3 4d subshell, with L is equal to 4 4f subshell. Dear children, here you need to identify that principal quantum number is explaining about orbit, and whereas azimuthal quantum number is explaining about orbital. N represents orbit or shell, L represents subshell, this is nothing but orbital. Now let us go for another quantum number, magnetic quantum number, which is represented with the symbol EML. The magnetic quantum number ML values indicate the number of orbitals in a subshell with a particular L value, and the magnetic quantum number has integer values between minus L and plus L including 0. For certain value of L there are 2L plus 1 integer values of ML as follows: minus L plus 1, so on, minus 1, 0, 1 and so on, plus L, minus 1 and finally plus L. These values describe the orientation of the orbital in space relative to the other orbitals in the atom. When L is equal to 0 then 2L plus 1 is equal to 1 and there is only one value of ML. Thus, we have only one orbital, that is 1s orbital. When L is equal to 1 then 2L plus 1 is equal to 3, that means ML has three values, namely minus 1, 0, plus 1. It indicates the three p orbitals with different orientations along x, y, z axis. These are labeled as px orbital, py orbital, pz orbital. Children, px, py, pz, all these three orbitals are belongs to the same subshell. Similarly, they are also belongs to the same shell. The orbitals which are belongs to the same shell or same subshell will have same energy, and the orbitals those are having same energy are called as what? Yes, these orbitals are called as degenerated orbitals. What are degenerated orbitals? Orbitals in the subshell belonging to the same shell with same energy are called degenerated orbitals, means these are having same energy. For example, Px, Py, Pz orbitals are degenerated orbitals because they have same amount of energy and also they belongs to the same shell. Here you can find L value, subshell and number of degenerated orbitals. L is equal 0, then subshell is S, the number of degenerated orbitals are 1. If L is equal to 1, then the subshell indicates P, number of degenerated orbitals are 3, then L is equal to 2, subshell is D, number of degenerated orbitals are 5. If L is equal to 3, then the subshell is F and the number of degenerated orbitals are 7. Like this, if L value increases, number of subshell will increase, obviously number of degenerated orbitals also increases. Magnetic quantum number explain the shape of orbitals. S orbital is spherical in shape, p orbitals are dumbbell in shape, d orbitals are double dumbbell in shape. Similarly, f orbitals are complex in shape. Children, you can find here the shape of s orbital, how it is looking. It is like a sphere. It is a 3D diagram, but whenever you want to draw, you can draw like this, simple like a circle, and you indicate x axis, y axis and z axis. Here you can find shape of 1s orbital and similarly shape of 2s orbitals. You can notice between 2s and 1s orbital there is a gap which is indicated with a white color circle. That is nothing but what, children? It is a node. Now you can see the shape of p orbitals, px, py, pz. Individually they are represented and all 3 p orbitals together also represented. So what is the shape of p orbital? It is dumbbell shape. You can draw like this. Simply whenever you want to draw, you can draw like this, px orbital, py orbital and pz orbital. Now go for shape of d orbital. D orbitals are double dumbbell shape. There are 5 orbitals, d yz orbital, d xz orbital, d xy orbital, d z square orbital, d x square minus y square orbital. These are all double dumbbell in shape, and whenever you want to draw, you can draw like this. Simply you can draw like this. See here the tabular form, n value is given, L value is given, ML value is given and subshell is indicated, number of orbitals in the subshell also indicated. Look at the table. First row, n is equal to 1, L is equal to 0, ML is equal to 0, subshell is 1s orbital, number of orbitals in the subshell is 1. If n is equal to 2, then L value 0, ML value 0, subshell is 2s and number of orbitals also 1. You remember here, if L is equal to 0, obviously number of orbitals in the shell subshell will be 1. If L is equal to 1, the number of orbitals will be 3 because ML values will be 3, minus 1, 0, plus 1. If L value is 2, look at that last column, n is equal to 3, L is equal to 2, ML is equal to minus 2, minus 1, 0, plus 1, plus 2, and that subshell is 3D subshell and the number of orbitals in the subshell is 5. How many magnetic quantum number readings are there? That many number of subshells will be there, orbitals will be there in the given subshell. Look at this. Here n value given 4. Here also you can find 4 different L values, L is equal to 0, 1, 2, 3, and ML values it varies 0, minus 1, 0, plus 1, minus 2, minus 1, 0, plus 1, plus 2, and especially focus on the last row, n is equal to 4, L is equal to 3 and ML values are minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3. And what is that subshell? 4f. and how many number of orbitals are there in the subshell? 7. So, this is about magnetic quantum number. Each subshell holds a maximum of twice as many electrons as the number of orbitals in the subshell. Each orbital accommodates 2 electrons. There is 1 orbital in S subshell, therefore, it accommodates only 2 electrons, but there are 3 orbitals in the P subshell, 3 2s are 6, therefore, how many electrons will be accommodated? 6 electrons. Similarly, in case of d orbital, d subshell, there are 5 orbitals, so 5 2s are 10, so d subshell can accommodate 10 electrons. Similarly, f orbital, there are 7 orbitals in f subshell, 7 2s are 14, 14 electrons can be accommodated in f subshell. The maximum number of electrons that can occupy various subshells is given in the following table. You see here. Now, let us go for another quantum number, that is spin quantum number. Spin quantum number indicates the property of electron. The spin quantum number refers to the 2 possible orientations of the spin of an electron. One is clockwise and other is anti-clockwise. It means while electron is revolving around the nucleus, it has its own spin, it rotates itself. That rotation may be in clockwise direction or it may be in anti-clockwise direction. You can find here spin in clockwise direction is indicated with +1/2 symbol, spin in anti-clockwise direction indicates a -1/2 symbol. These are represented by +1/2 and -1/2. If both are positive values, then the spins are parallel, otherwise the spins are anti-parallel. The importance of the spin quantum number is seen when electrons occupy specific orbitals in multi-electron atoms. Children, how these electrons are distributed into the various atomic orbitals, that was given in electron configuration. So, now see that electron configuration. The distribution of electrons in shells, subshells and orbital of an atom is known as electron configuration. Electronic configuration of different atoms is represented with the notation NLX. NLX. Here the shorthand notation consists of the principal energy level, means N, the letter represents subshell L value, and the number of electrons, that is X, in the given subshell. For example, consider the hydrogen atom with atomic number 1. The electron configuration is 1s1. Here 1s1 is written in the form of NLX method. Here the 1 which has written as first, that indicates the principal energy level, it means it is the first shell. S, whatever we have written, that indicate the subshell L value, the subshell L is equal to s orbital, and the number of electrons in the subshell is only 1, that is written in the form of superscript. See the diagram. In an hydrogen atom, there is only 1 proton and only 1 electron. Proton is in the center of the atom and electron is revolving around the nucleus. The electron configure 1 electron, that is why that is indicated with upward arrow mark. And in case of helium, there were 2 electrons. One is indicated upward arrow mark and other is indicated with downward arrow mark. And if you see the electron configuration of hydrogen, then n is equal to 1. See the 4 quantum numbers of the electron which is present in hydrogen. N is equal to 1, L is equal to 0, Ml is equal to 0, and spin quantum number, that is Ms, is equal to 1/2. It may be +1/2 or it may be -1/2. To describe the electron configuration for more than 1 electron in the atom, we need to know 3 principles, that is Pauli's exclusion principle, Above principle and Hund's rule. By knowing these 3 rules, you can write the electron configuration of other atoms. What is Pauli's exclusion principle? What it says? According to Pauli's exclusion principle, no 2 electrons of the same atom can have all the 4 quantum numbers the same. The major consequence of the exclusion principle involves orbital occupancy. Since only 2 values of the spin quantum numbers are allowed, an orbital can hold only 2 electrons and they must have opposite spin. Electrons with paired spins are denoted by upward arrow mark and downward arrow mark. One electron has plus 1 by 2 and other has minus 1 by 2. The anti-parallel spins electronic configuration of helium atom is given here, and here you can see that one is upward and another is downward, or you can write it as 1s2. For hydrogen we have written it as 1s1, and now for helium it is 1s2. What is above principle? Electron configuration can be written by placing electrons in the lowest available orbitals first until it is completely filled, then the electron enters into the higher energy orbital. In simple words, you can say that the lowest energy orbitals are filled first. So, electrons goes into the lower energetic orbital. The maximum number of electrons in any shell is equal to 2n square. N is the principal quantum number. The maximum number of electrons in any subshell like SPDF is equal to the 2 into 2L plus 1, where L is equal to 0, 1, 2, 3, 0 for S, 1 for P, 2 for D and 3 for F orbital. Thus, these subshells can have a maximum of 2, 6, 10 and 14 electrons respectively. Two general rules help us to predict electron configurations. One is, electrons are assigned to orbitals in order of increasing value of n plus L, and the second one is, for subshells with the same value of n plus L, electrons are assigned first into the subshell with lower n value. Children, you need to remember this task is very important. Here, in which orbital we have to write the electrons first? We know that first we have to write the electrons in the lowest energetic orbital. Then how do we know? For example, 2s orbital is there and 1s orbital is there. Among this, electron should fill only in the 1s orbital, because n plus L value of 1s orbital is equal to 1, because n is 1 and s orbital L value is 0. Therefore, n plus L value it will become 1. For 2s orbital it is 2 plus 0, it means it is 2. Which is lower? In case of 1s orbital, n plus L value is less, that is why we have to write first electron in 1s orbital and even second electron also in 1s orbital. If n plus L values are same, then in which orbital we have to fill the electron? For example, in case of 3p orbitals and 4s orbital, n plus L value of 3p orbital is 4 and n plus L value of 4s orbital is also 4. In this case, in which orbital we have to fill the electron first? Obviously, for which orbital smaller n values are there, there we have to fill the electrons. 3p n value is 3, 4s n value is 4. So, therefore, we have to fill the electrons first in case of 3p orbital. Ascending order of energies of various atomic orbitals is given below. 1s is less than 2s, 2s is less than 2p, 2p is less than 3s, 3s is less than 3p and it is less than 4s, it is less than 3d and it is less than 4p, it is less than 5s, it is less than 4d and it is less than 5p and it is less than 6s and so on. You can find a diagrammatic representation of increasing energy of atomic orbitals. First electron goes to 1s, then the next two electrons goes to 2s, then electron goes to 2p, then 3s, then 3p, then 4s, then 3d and 4p and 5s and so on. This representation, this kind of representation is called Euler's diagram, or it is also called Euler's chart. The electron configuration of some elements in the increasing atomic number, that is Z value, is given below. See children, here I have written electron configuration for hydrogen, helium, lithium, beryllium and boron. For hydrogen it is 1s1, for helium 1s2, for lithium 1s2, 2s1, for beryllium 1s2, 2s2, boron 1s2, 2s2, 2p1. Children, you focus here. After helium, I have written 1s2, 2s1. Why I have written third electron in 2s orbital? Because s orbital can accommodate only 2 electrons. Obviously, the third electron goes to next orbital. Similarly, in case of boron, you see 1s2, 2s2, 2p1. After 2s2, the fifth electron gone into 2p orbital. Now, let us see the Hund's rule. What is Hund's rule? According to this rule, electron pairing in orbital starts only when all available empty orbitals of the same energy are singly occupied. It means degenerated orbitals should equally fill the electrons. For example, see the electron configuration of carbon atomic number 6, and electron configuration can be written as 1s2, 2s2, 2p2. Focus here on 2p2. There are 2 electrons in 2p subshell. They did not pair up and both are having parallel spin. See, both electrons are indicated with a upward arrow mark. It means as these orbitals are equal energetic orbitals and they should fill equally, then only the pairing will be starts. The unpaired electrons in 2p orbitals are shown with parallel spins. Consider sodium atom with atomic number 11. The electron configuration is 1s2, 2s2, 2p6 and 3s1. It can be written like this. S indicates subshell, 1 indicates principal quantum number, and the number 2 indicates number of electrons in the given subshell. See the electron configuration of remaining are given in the following table. You see here. Here from carbon to magnesium it was given. Carbon atomic number 6, electron configuration 1s2, 2s2, 2p2, and for magnesium 1s2, 2s2, 2p6, 3s2. Aluminum atomic number 13, electron configuration 1s2, 2s2, 2p6, 3s2, 3p1. Potassium atomic number 19, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Calcium 20, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Children, I hope that you have understand how to write electron configuration. We practice once and twice, then you will be getting how to write the electron configuration very easily. And let us conclude the lesson by revising today's class. It is not possible to measure accurately the position and velocity of an electron continuously. We have learned that the space around the nucleus where the probability of finding the electron is maximum is called orbital, and we have studied about quantum numbers and which indicates energy, shape, orientation, and we also studied about arrangement of electrons in the shells, subshells and orbitals, which is called as electron configuration, and also we studied about Pauli's exclusion principle. No 2 electrons of the same atom can have all the 4 quantum numbers same. Above principle, the lowest energy orbitals are filled first. And what is Hund's rule? The orbitals of equal energy are occupied with 1 electron each before pairing of electron. Children, try to answer the following question and improve your learning. What information does the electron configuration of an atom provide? What is an orbital? How is it different from Bohr's orbit? Means write the difference between the orbit and orbital. Explain the significance of 3 quantum numbers in predicting the position of an electron in an atom. What is NLX method? How is it useful for you? Which rule is violated in the electron configuration? 1s0, 2s2, 2p4. Write the 4 quantum numbers for the differentiating electron of sodium atom. Please download worksheet from SIET for better practice. Thank you children. Have a nice day.